Hello there, Mr. Sutton here with the AB Calculus 411 Extra Practice Number 2 solutions on L'Hopital's rule. For this one, we're trying to find the limit of this expression. So one thing I'm going to do before I do anything else on this one, just to make my life a little bit easier, this sine cosine is actually part of an identity. I know that 2 sine cosine is the same as sine of 2x, so 1 sine cosine is really the same as 1/2 sine of 2x. And this is going to make our life a lot easier down the road on this problem. You might not realize it yet, but just trust me on this one. All right, so if we want to evaluate this limit as x equals 0, well, if you plug in 0 mentally real quick, you'll notice that we get 0 over 0, the indeterminate form. So in order to wrestle with that, we have to use L'Hopital's rule, and we're going to have to show that the limits are individually 0. So the limit of the numerator as x approaches 0, sine of 2 times 0 is 0. That's going to zero out this whole thing, so that definitely comes out to 0. And then the limit as x approaches 0 of the denominator, well, you're plugging 0 in here. Cosine of 0 is 1. 1 minus 1 is 0. So these both definitely come out to 0. So using L'Hopital's rule then, because we ended up with 0 in the numerator and the denominator, let's take the limit as x approaches 0 of the derivatives of the top and bottom. So this is where turning sine cosine into 1/2 sine of 2x is going to help us out, because now we don't have to deal with the product rule. So this is going to be, let's see, 1/2 cosine of 2x times a tail of 2. So that ends up just being cosine of 2x, which is pretty nice. And then downstairs, cosine of x is going to be negative sine of x, and that 1's gone because it's just going to become a 0. So now if we plug in 0 again, we're not going to get 0 over 0 this time. So let's go ahead and evaluate what this comes out to now. Cosine of 2 times 0, well, that's really cosine of 0, which is going to come out to 1. And sine of 0, negative sine of 0, that still comes out to 0. So this is undefined, so that means that our limit then does not exist. For this problem, if you try to take the limit of this one as x approaches 0 by just plugging 0 in for x, you're going to see that we end up with the indeterminate form. So to get around that, we're going to take the limit of the top and bottom individually, and then we're going to use L'Hopital's rule. So limit of sine of 2x as x approaches 0 is going to be 0, because it's really just the sine of 0. And we're going to get the same result as x approaches 0 for the denominator there. But we have to show both of these in order to justify using L'Hopital's rule. So using L'Hopital's rule now, because the numerator and denominator have both been shown to have limits of 0, we're going to take the limit as x approaches 0 of the derivatives now. So for the numerator, using the chain rule, this is going to be 2 cosine of 2x. And for the denominator, same deal, except now we're going to have 3 cosine of 3x. And if I plug 0 into each of these individually, I'm not going to get 0 over 0 this time around. I'm going to get, let's see here, cosine of 0, which is 1, but we have a 2 multiplier up here, so that's a 2. And then down here, this is going to be 3 times 1, so that's 3. And that's not 0 over 0, and it's a constant, so we're done. For this one, trying to find the limit as x approaches 0, we're going to see very quickly that we end up with 0 over 0, the indeterminate form, if we just try plugging in 0. So to get around that, we're going to have to use L'Hopital's rule. But before we can use it, we have to show that the limits of the numerator and denominator are both 0. So now limit as x approaches 0 of sine squared of x, well, that's just really sine of 0, which is 0. Squaring that also gives us 0. So that definitely equals 0. And then limit as x approaches 0 of x is just 0. So now using L'Hopital's rule, now that we've shown these two limits separately, we're going to take the limit as x approaches 0 of the derivatives of these two functions. So numerator, we've got 2 times the sine of x times the derivative of sine, which is cosine of x. And then derivative of x down here is just going to be 1. Now, if I had to keep going, I would probably convert this 2 sine of x cosine of x to sine of 2x, but I know I'm pretty much done, almost done on this problem, because I have something that's not 0 definitely in the denominator here. So all I have to do at this point is plug in 0 to sine of x cosine of x. Sine of 0 is going to be 0. That zeroes out the whole numerator. So this whole thing just comes out to 0 over 1, or just simply 0. For this one, we want the limit as x approaches -3 of this rational radical function. So if you plug in -3 directly for x, you're going to end up with square root of 2, or square root of 4 rather, which is 2. Minus 2 is 0 in the numerator. And we have -3 plus 3, 0 in the denominator. So that's no good. We're going to take a step back and show that the limits of these two terms are individually 0, because that will allow us to then use L'Hopital's rule to evaluate this limit. So I've got limit of the numerator as x approaches -3. And again, this is really just going to be the square root of 4 minus 2, which comes out to 0. And then limit as x approaches -3 of our denominator. -3 plus 3 definitely comes out to 0. So then, using L'Hopital's rule, we take the derivative of the top and the bottom separately, and we still have a limit as x approaches -3. So for the numerator, this function is really x plus 7 to the 1/2 power. So I'm going to have, for the derivative, 1/2 x plus 7 to the -1/2. And there's no tail to worry about, because the derivative of x plus 7 is just 1. In the denominator, derivative of x plus 3, that's just going to be 1. And the -2 and the 3 just get zeroed out, because you're taking the derivative of constants there. So we just have 1 in the denominator. So now, plugging in -3, I can rewrite this as, let's see here, 1 over 2 times the square root of -3 plus 7, or the square root of 4. So square root of 4 is 2. 2 times 2 is 4. Hence, 1 over 4. On this one, we're trying to find limit of this expression as x approaches 0. Now, if you just plug 0 in right off the bat, everything gets zeroed out, and we have the indeterminate form 0 over 0, which we're not going to write. So one way you could deal with this is to use L'Hopital's rule. Another way, though, a little bit more efficient, would just be to factor and cancel some things out. So in the numerator, we can factor out an x squared, leaving us with 5x plus 8. Denominator, we can also factor out an x squared, leaving us with 3x squared minus 16. And now these x squareds cancel, leaving us with just the stuff in parentheses. At this point, if you plug in 0 again, everything with an x is still going to cancel out, but now we're going to have an 8 and a -16 left over, which, if we want, we can reduce to -1/2. For this complex fraction, we're trying to find the limit as x approaches 0. Now, just mentally plugging 0 in for all the x's, numerator is going to be 0. Denominator, you've got 1/3 minus 1/3, which is also 0. So to avoid writing the indeterminate form, we're going to have to use L'Hopital's rule. But before we do that, we have to show that the limits of the numerator and denominator are both 0. So let's start with the numerator. Limit as x approaches 0 of x is just 0. And limit as x approaches 0 of the denominator. Again, this is going to be 1 over 3 minus 1 over 3, which comes out to 0. Using L'Hopital's rule then, let's go ahead and take the derivatives of the top and the bottom separately. So I've got the limit as x approaches 0, still have to have that. And derivative of x, that's pretty easy, that's just 1. But now we have to take the derivative of 1 over 3 plus x, and this 1/3 we don't have to worry about, that's just going to be 0. But this one here, well, this is really 3 plus x to the -1 power, whose derivative is negative parentheses 3 plus x to the -2. So just using the power rule there. And I can actually move this whole thing up to the numerator with a positive 2 exponent and plug in 0 while I'm doing it. So this then just ends up being -9. To take the limit of this expression as x approaches infinity, I'm just going to choose my champion here. In the numerator, 2x is the dominant term. In the denominator, it's 4x, growing faster than the constant. So just reducing this, we end up with 1/2. To find the limit as x approaches infinity of this rational function, I'm going to choose my champion since I have a limit to infinity. So in the numerator, the dominant term is going to be this -2x to the 4th, while in the denominator, x is the fastest growing term. I can reduce this now. So this is going to be -2x cubed. Still have the limit as x approaches infinity. And if I essentially plug infinity into this, this is all going to grow to -infinity. To find this limit as x approaches 0, we first consider what would happen if we just plug 0 in, which would give us 0 in the numerator, and, well, ln of 1 is also 0 in the denominator. So we're not going to do that. Instead, we're going to show that the limit of the numerator and denominator are both 0, and then we're going to use L'Hopital's rule. So limit as x approaches 0 of 3x, we know that's going to come out to 0. And limit as x approaches 0 of ln of x plus 1. Again, ln of 1 just is 0, so this whole thing comes out to 0. And we have to show these before we can use L'Hopital's rule. But now that we've shown them, using L'Hopital's rule, let's go ahead and take the limit as x approaches 0 of the derivative of both of these. So we've got 3 in the numerator, and then in the denominator, we've got 1 over x plus 1. Now, I know I'm not going to get 0 over 0, so I'm just going to go ahead and plug in 0. So this is going to be 3 over, let's see here, this would be 1. So that all just comes out to 3. For this problem, if you try just plugging infinity into this, you're going to have an infinity over an infinity, which is no good. So what I'm going to do, I'm going to rewrite this as 4x over e to the x. And I see here, actually, that e to the x is a faster growing function than 4x. This is a bottom-heavy function as we go to infinity. So this is just automatically going to come out to 0. For this problem, trying to find the limit as x approaches 0 of this craziness. Now I can see, just kind of mentally plugging in 0, sine of 0 is going to 0 out everything in the top. The bottom, we're also going to end up with 0. So to avoid that, I'm eventually going to want to use L'Hopital's rule. But before I do that, let me clean this up a little bit, because L'Hopital's rule involves taking derivatives, and if I can avoid using the product rule, I'm going to avoid it. So just distributing this sine of x, we have sine of x minus sine of x cosine of x. And one way, so I still have a product rule kind of waiting in the wings right here. To avoid that, I'm going to rewrite this as minus 1/2 sine of 2x, just using my double angle identity that I often use whenever I see sine of x times cosine of x. Because 2 sine of x cosine of x is the same as 1 sine of x, 1 sine of 2x. Okay, so now I have to show that my limits of my numerator and my denominator are both 0. Otherwise, I'm not allowed to use L'Hopital's rule. So limit as x approaches 0 of the numerator, all of this stuff. This is going to be sine of 0, which is 0, minus basically another sine of 0. So that all does come out to 0. And now limit as x approaches 0 of 2x squared, the denominator, definitely also coming out to 0 if you plug 0 into that. So then using L'Hopital's rule, I have the limit as x approaches 0 of the derivatives of these two functions. So upstairs, derivative of sine is cosine of x. And then this next one's going to require a little bit of a chain rule. So this is going to be negative 1/2 cosine of 2x times 2 because of this inner derivative of 2. So that ends up being just minus cosine of 2x, which is kind of nice. Downstairs, we've got 4x taking that derivative. And just kind of mentally plugging in 0 again, I've still got 0 in the denominator. And upstairs, this is going to be 1 minus 1, which is also 0. So we're going to have to use L'Hopital's again. And I'm again going to have to show that the limits of the numerator and denominator are both 0. So here we go again. Limit as x approaches 0 of my new numerator here is going to come out to 0, because again, we're doing basically 1 minus 1. And limit as x approaches 0 of 4x, 4 times 0 is going to come out to 0. So using L'Hopital's rule, hopefully for the last time, derivative now of the numerator, and this is still limit as x approaches 0, derivative of the numerator, we've got a negative sine of x, and another chain rule here, so this is going to be negative, or actually positive, because a negative negative, so positive 2 sine of 2x, all of that over just 4. Now, since I've got something that's not 0 in the denominator, I know I can just plug 0 in at this point. I'm not going to have to use L'Hopital's again. So just plugging 0 in, we've got 0 for this sine term, 0 for this other sine term. So this just comes out to 0 over 4, which is just plain old 0.